Hello everyone, welcome back. In the last class we looked at some advanced schemes. We looked at the schemes which are basically Lax-Frederick, Leapfrog, Lax-Vendrau, beam warming and so on and so forth. And we saw that basically they are kind of variations of FTCS scheme, forward in time and certain space. And then basically because of those variations these schemes become stable. The other interesting thing that we saw about these schemes is that you can basically control the diffusion and the dispersion error by basically smartly manipulating the first error term, right. So, the leading error term, and we found that for example, Lax-Vendrau is a scheme which does not have dissipation error in the leading term, it is a dispersive error. So, it is supposed to give you a better accuracy compared to let us say FTBS scheme, and also it is stable unlike the FTCS scheme which is unstable, right. But it has dispersive error, that means you should not have any mistake in the initial condition, or even if the some perturbations come from the initial condition, it might grow, it will not decay because it has got the dispersive error. And Lax-Frederick at the same time we saw that it is highly dissipative, it is also stable, but it is first order. And then we had the Leapfrog scheme which was the 3 level time stepping scheme, and we found that this is also stable for lambda less than equal to 1, and it was like the order of accuracy was delta x square. Okay. So, today we are going to see some more schemes. So, why we need more schemes? That most of the schemes that we saw actually they have been derived if you look at closely. So, we have like del u by del t plus c del u by del x equal to 0, this is the linear convection scheme. So, you would note that many of the schemes have been derived by considering u t equal to minus u x, and then u t t, I mean by manipulating this becomes c u c s u x x, right. If you go from the non-linear problem to non-linear problem, del u by del t plus now it is u del u by del x equal to 0. Okay. So, this is linear and this is non-linear. Okay, we have talked about this great deal. There are many ways to look at it. The non-linearity in this one is that you can write it del e square by 2 delta x equal to 0. Okay, that is a non-linear problem. Okay, secondly, you can look at the character, the coefficient of the gradient term, and that depends. So, the speed at which it is convecting also depends on the solution of the problem. Third way to look at it is that if you let us say u1 and u2 are two solutions for this, okay, u1 plus u2 will also be a solution. Okay, here. Okay, here the same is not true. Okay, if u1 and u2 are separately solution for this, u1 plus u2 will not be the solution, right. Now, if you want to derive schemes like let us say Leapfrog or the Lax-Vendrau schemes, the first roadblock that you will hit is that now this u t equal to minus u u x, okay, and if you take the second derivative u t t, you will have to take the derivative of both basically u and u x, okay, it will have 2-3 terms, right. So, you cannot get this relation like you have this u t t equal to c square u x x. So, that means the relations that you have derived are not so straightforward. Okay. For example, in the beam warming scheme or even in the Lax-Vendrau scheme, if you recall what we have used that we had this u x x term theta by 2 u x x term, this is the value dissipation that we had added on the right hand side, and we found that in order the scheme become stable, the theta should be equal to lambda square. Okay. So, this was FTCS and plus this part, right. And for u x x we had basically used the our u I plus 1 minus 2 u I plus u I minus 1 by delta x square, right. And this was our Lax-Vendrau scheme. It cannot be easily derived for the nonlinear problem because your u t t is not equal to c square u x x. Okay. That is not true for the nonlinear problem. Okay. So, but we can basically what we can do, we can break this problem into two steps. Okay. this scheme into 2 steps, and that is what we are going to do. So, this is will be called the multi-step method. Okay. So, what advantage you will have? So, it will have 2 steps, okay, step 1 and step 2. Okay. So, first we can use some scheme, okay, let us say scheme 1, okay, and you can basically use intermediate value you are getting. So, you can use maybe the time step of delta t by 2 here, and then delta 2 by 2 maybe the perhaps in the second step, and you can combine it to get your method, right. So, these kind of approaches are called multi-step methods. Okay. I am doing it showing it for 2, but you can also have 3 steps. Okay. Now, you can basically combine different schemes and get maybe one of these schemes for a linear problem, right. For the non-linear problem it will be very different, but for the linear problem you can let us say go back to let us say Lax-Van-Derp scheme, and I will give you some examples today. Okay. So, the another advantage of this multi-step method is that when the problem is non-linear, let us say look at this example. Okay. So, your variable the speed at which the variable is travelling also depends on the variable itself, right. So, that means it will eventually develop a shock. Okay. So, it is travelling, and as it increases, so it will become closer and closer and closer, and it will ultimately become a shock, right. And in this kind of shocks, many of the methods that we have discussed earlier, the simple method will not work, right. So, we can combine 2 steps. For example, in one step we can go forward, and we can other step we can go backward. So, if we use that kind of methods, then that approach may work for this problems which are highly nonlinear. Okay. So, that is another beauty of the multi-step method, that they work good for nonlinear problems. Okay. In fact, all the schemes that we have discussed so far, if you try using those schemes for solving problems like the Burger's equation or Euler's equation, or even the nonlinear convection equation, okay, you would see that those methods will fail. Okay. The scheme will I mean blow up very quickly, right. So, in order to solve those problems, you have to go to the multi-step method. This is a very important discussion, because most of the systems that we are going to solve will be nonlinear, including the Navier-Stokes equations, right. So, let us look at some of the multi-step methods. Okay. So, multi-step will have 2 steps. Okay. The first step we will call as the predictor step. Okay. So, that is the you will get some value which is not correct. Okay. We are just predicting some value, and then in the second step what we will do, we will call it the corrector step. Okay. So, first we predict, and then using that predicted value we will correct it. Okay. And for the nonlinear problem, these equations, these different discretization schemes in the prediction and corrector will provide stability, but for the linear problem they may be equivalent to let us say Lax-Van-Derp scheme, okay, for whatever cases that we are discussing today. Okay. So, I will be discussing 2-step Lax-Van-Derp. Why it is called 2-step Lax-Van-Derp? Because eventually if you combine the 2 steps for a linear problem, it will lead to a Lax-Van-Derp scheme. Okay. So, now we are splitting the Lax-Van-Derp scheme into 2 steps. Then there will be Richtmeier scheme. Okay. This also leads to Lax-Van-Derp with a slight change. Okay. The McCormack scheme, this also if you combine it will lead to Lax-Van-Derp, and the final is 2-step beam warming, that also leads to the 2-step Lax-Van-Derp scheme. So, I will discuss these 3 schemes today, and this I will leave it to you to basically go back and read about it. Okay. There it is also very similar to what schemes that we have. Okay. So, the first step is the Lax-Van-Derp scheme. Okay. So, let us discuss the Lax-Van-Derp scheme. So, the schemes I will discuss for the linear problem, but we can basically change it to the nonlinear problem also, the scheme remains the same. Okay. So, if this is linear problem, okay, the nonlinear problem can become del u by del t, and typically it is written as del f by del x. Okay, this is x is equal to 0, where if it is let us say nonlinear convection, then f is equal to u square by 2, right. Then if you put it there, then it will become del u by del t plus u del u by del x. Okay. So, whatever scheme that you are deriving, let us say I am deriving an FTCS scheme or writing an FTCS scheme for this, or FTBS rather, because that FTCS is not stable. So, this is ui n plus 1 minus ui n by delta t plus c ui n minus ui minus 1 n by delta x equal to 0. The same thing if you write for the nonlinear problem, you would write I will follow this one. And why I am following this one? Recall we had some discussions about the conservative form and the non-conservative form earlier. Okay. This is the non-conservative form and this is the conservative form, right. And we found that there are some properties if you use the conservative form. What are the properties? One is that if you use the non-conservative form in the discretized form, here you can use the FTCS or FTBS or whatever scheme that you want. If it is FTBS, this is ui minus 1. So, in that case, what will be the value of u? Is it ui or ui minus 1, right. So, that confusion is there. Secondly, we have talked about this telescopic collapse when you are using this form, the conservative form instead of the non-conservative form, right. So, basically if you add it from end to end the discretization scheme in a conservative form, so all intermediate fluxes will vanish, on only the boundary conditions or the end fluxes will remain. Basically, the things going in is what is coming out, right. If you use the non-conservative form, you cannot basically guarantee that. Okay. So, if you use a conservative form, so let us remove this non-conservative form now. Okay. If you use a conservative form, this equation can be written as ui n plus 1 minus ui n by delta t plus, let us say it is FTBS. So, this is fi n minus fi 1 minus n by delta x. Okay. So, you can see this is for the linear equation, this is for the nonlinear equation where I have used the conservative form. Okay. So, all the discussions, all the schemes that I will be writing is for the conservative for the linear, but you can write equivalent nonlinear form. Okay. So, we were talking about the two-step Lax-Pondorf. Okay. So, what we will do in this is that, so we will have two steps, right. So, this is let us say my I n, and then we will have something in between. Okay. I will call it n plus half, okay, and then we are supposed to go to n plus 1. So, I created an artificial step in between, okay, and then this is my grid point, this is I, this is I plus 1 and this is I minus 1, right. In the two-step Lax-Pondorf, we will also create two intermediate grid points, okay, which will be I plus half and be I minus half. Okay. So, if you use this scheme, now first step in this is basically that is the Lax scheme or basically Lax-Frederick scheme. Okay, that is step 1. Okay. So, you know the what is Lax-Frederick scheme. So, for this problem if you write the Lax-Frederick scheme, that will be u I n plus 1 minus u I n will be half of u I plus 1 n and u I minus n, right, and by delta t is equal to minus c, and this is central on the right side. So, u I plus 1 n minus u I minus 1 n by delta x. Okay. So, you now use the Lax-Frederick scheme, but do it on I by 2, okay, I plus half, okay, and also n plus half, right. So, we are using delta t by 2 because we are going for the first step, and we are also using delta x by 2. Okay. So, if you use these two, so this thing, so now if I am doing it let us say I plus half. Okay. So, when we are doing this I n plus 1, what were the nodes that we are participating? So, for the full one we are participating this I plus 1 and I minus 1, right, to get the n plus 1. Now, if you are doing it for I plus half, then the nodes participating will be I plus 1 and I, right, because we are trying to get it for I plus half. So, write the same thing for delta t by 2 and delta x by 2. Okay. So, it will become let me use a different pen. So, this is u I plus half will be n plus half minus half. Okay. This is now the nodes participating will be I plus 1 and I. Okay. So, u I plus 1 n plus u I minus 1 n by delta t now is delta t by 2, right, because you are doing for the only half the grid size, right. This is a minus c, and then this will become u I plus 1 n minus u I n by this will be delta x by 2. Okay. So, it was 2 delta x here. So, this will become 2 delta x by 2, right. So, you can get the value u I plus half n plus half would be equal to half u I plus 1, this will be I, right, n plus u I n minus. So, this 2 will cancel out. So, you can write it, this will be lambda by 2 u I plus 1 n and minus u I n, right. So, this is my first equation. Okay, let me just see if I have done it correctly. Okay, so, this is I plus 1 and I delta x by 2 and this becomes c delta by 2. Okay, looks fine. Okay, let us go to the second step. Okay, I will do it here only because I have not basically kept many pages. So, let me just clear this out. Okay. So, the step 2, okay. Step 2 will be the leapfrogging at n plus half. Okay. So, let us do the leapfrogging at n plus half, and so leapfrogging scheme that you have will be, if you have a full stencil, okay, in the normal condition your leapfrog scheme looks like u I n plus 1 minus u I n minus 1 by delta t, this will be 2 delta t will be minus c u I plus 1 n minus u I minus 1 n by 2 delta x, right. This is leapfrogging central in time and central in space. Okay. But now we are doing it n plus half and we are only doing for delta by 2. So, now it looks so when we had this is a 3 level scheme. So, we had n minus 1 and this was n plus 1, right. To get the value at n plus 1 we needed the value at n as well as n minus 1. Now, if you are doing it n plus half, so the 3 levels that we have is n plus half and n plus 1, right. So, write the scheme for that. So, this will become u I n plus 1 minus u I n minus 1 in this case will be n, right, minus u I n by 2 into delta t by 2, right, that will become minus c, and then you have you will use u I plus half, okay, n minus u I minus half, this is n plus 1 by 2 and n plus 1 by 2. Okay, so we are doing this leapfrogging at n plus 1 by 2 into delta x by 2, right. So, this is our 2 scheme. So, finally, you can write your u I n plus 1 would become, so all these things will cancel out. Okay, this will become u I n minus c delta t by delta x, which is basically nothing but lambda u I plus half n plus half minus u I minus half n plus half, right. So, this is how you will obtain your the corrector step. So, this is my corrector step, okay, and this is my predicted step. Okay. Now, for a linear problem you can combine both of these, and you can see that it leads to basically nothing but your Lax van der Waals scheme. I will just show it. Okay. So, let us try to write u I n plus 1 is u I n minus c delta t by delta x, that I will write lambda, okay, and that u I plus half n plus half. So, what will be the value? We can write this value. Okay. Okay, so the value will be half u I plus 1 n plus u I n minus lambda by 2, okay, u I plus 1 n minus u I n, right. This is the value of u I plus half. Now, do it for u I minus half. Okay, so that will be minus, use the bracket here, and for u I minus half, what will the nodes participating? Okay, in this case, if you change it for u minus half, that will be I minus 1 and I, right. So, this is u I n plus u I minus 1 n minus lambda by 2, okay, u I n minus u I minus 1 n, right. So, this is your second term. Okay, so you can combine both of them. So, u I n, I am collecting all the lambda terms, okay, minus. So, this is my lambda term, this is my lambda term. So, minus lambda by 2, okay, and that will become u I plus 1 n, and that is minus u I minus 1 n, right. This is, and then we have lambda square by 2, right, and that you can combine these two. So, this is u I plus 1 n minus 2 u I n and plus u I minus 1 n, right, and you can see that this is your nothing but Lax van der Waals scheme. Okay. So, for a linear problem, the two step Lax van der Waals goes back to the Lax van der Waals scheme. Okay. But in this we have two steps, one is the predictor and one is the corrector. The first we use the Lax-Frederick and second we use the leapfrog, right. And because it leads to the Lax van der Waals scheme, it has the same stability as the Lax van der Waals scheme, that means it is stable for is the second order accurate scheme, and this is single step Lax van der Waals, and stability limit is basically lambda less than equal to 1, as we have discussed earlier. Okay. Now, let us go to the Richtmeier scheme. Okay. Now, in Lax van der Waals we saw that we have to do lot of bookkeeping. Okay. So, we have to basically use I, and then you have to use I plus half, okay, and then I minus half, okay, and so on and so forth, right. So, basically even though your grid is I plus 1, I minus 1 and so on and so forth, you need to basically create intermediate grid points and store the values there, and they use that in the next step and so on and so forth, right. What Richtmeier did is basically remove this dependency on I plus half and I minus half, and he basically used this both Lax-Frederick and the leapfrog in the regular stencil only, right. So, this is the scheme that they have. Okay. So, the first step, this is my n, okay, let me write this is n plus half, this is n, this is n plus 1, and this is my I plus 1, and this is I minus 1. Okay. So, first step same thing, okay, do the Lax-Frederick at n plus half. So, this is my n plus half that we are trying to calculate. Okay. So, if you use this at n plus half, okay, so this stencil will be at I plus 1 and I minus 1, and then you instead of delta t, you are just marking the delta t by 2, right. So, we are just going here, okay, this and this we are going here. Earlier we are going from I minus half to I plus half, right. So, this is the scheme that we will get, and next you do the leapfrogging with delta t by 2 at n plus half as we did earlier, right. So, if you do the same thing, so now your this is our central point, this is forward, this is backward. So, you can use this, this will become u I n plus 1 minus u I n by delta t by 2, right, and that will become minus u I plus 1 n plus half minus u I minus 1 n plus half, okay, and that will be delta x, right. This will be 2 delta x, okay. I think there is 2 missing here, okay, yeah. So, then if you combine that these two, okay, it will become a leapfrog like a scheme, but there will be slight difference, okay. So, first we go from this to this and then you do the leapfrogging for the next delta t by 2, okay. So, first you use the delta t by 2 to only arrive here and then use these values to get the value at n plus 1, okay, at this point. Okay, so, this is my u I n plus 1. So, you will get u I plus 1 n plus 1, u I minus 1 n plus 1, use this value to get the next step. Okay. So, this is the Richtmeier scheme, and if you combine both of them, okay, so you will get a scheme which looks like Lax Van Drop, but now it is instead of 3 points it is 5 points. Okay. This is I plus 1 and I minus 1, this is what our Lax Van Drop was. It was I minus plus 1 I minus 1, this is I plus 1 I minus 1 and 2 u I. Now, instead of that, please go back and combine this, you will get I minus 2 and I plus 2. Okay. So, this is the kind of scheme that you will get, okay. And because now you are jumping 4 stencil, so this will become 4 delta x instead of 2 delta x, and here correspondingly it will become 8, okay, the denominator will become 8. Okay. And if you go and plot the stability for this, and you will see that this is stable for lambda less than equal to 2. Okay. So, you can go up to the value of 2, but remember, because we are using this we are taking I plus 1 and I minus 1 on both the steps. Okay. So, your accuracy may go down at the boundary, okay, because there you cannot use one sided step. Okay. And you are combining basically I plus 2 and I minus 2. Okay. So, this scheme is stable for lambda less than or equal to 2. This is also a second order scheme, delta x square delta t square, okay, like the 2 step Lax Van Drop. Okay. And this is a very popular scheme, especially if you have SOX, okay, or any nonlinear problem, any hyperbolic nonlinear problem. This scheme is very popular. Okay. In the next class, we will look at the McCormack scheme, and I will also show you some examples using these schemes. First, I will show you the examples for the linear problem. I will take you through this FTCS, FTBS and all schemes that we discussed in the last class, okay, and then I will show you for the non-linear problem. So, see you in the next class. Thank you very much.